Here we go again with another look at the shape of the Earth. Is it round or is it flat? This time I want to pay particular attention to a question I see sometimes. I see this on Quora a lot, see it on YouTube once in a while, and that is, how can we even know? How can we be so sure one way or the other? Well, if you've ever watched any of my stuff, you know that critical thinking is my main thrust. So what I really want to do here is use this as an example to, illustrate how critical thinking works so you can apply that to all kinds of stuff in your everyday life. So, when you first heard about the roundness of the Earth from your teacher, your parents, way back when you were just a kid, you probably just accepted it. But frankly, that's not good critical thinking. And now you troll on the internet, you see somebody, some stranger on the internet tells you that no, your teacher was lying and the Earth is actually flat. Well, now that we know that that's not critical thinking, we don't just accept what some stranger on the internet says. We demand more than that, right? In fact, I could argue that simply believing the teacher is a lot better, because at least you can make a reasonable argument that the teacher is a trustworthy person, whereas some stranger on the internet is not. Well, if you're saying to yourself right now, this guy's just some stranger on the internet, why should I listen to him? Well, that's good for you. You've passed the first test of you're starting to think critically. That's good. What is the difference? Well, the difference is I'm not going to tell you that the Earth is flat, and I'm not going to ask you to believe me. I'm going to tell you that you can figure this out by yourself if you just pay attention to the evidence. So that brings us to evidence. That's the first step, really, in critical thinking, is to demand evidence. We're not just going to accept what anyone tells us. We're going to need some evidence for that. But really, that's still not a passing grade in critical thinking, because I could just hand you a bologna sandwich and say, hey, here's the evidence the Earth is flat. This bologna sandwich proves it. That's not really going to cut it. Evidence is useless unless you can evaluate it. You need enough skill, enough knowledge, enough understanding of the situation to evaluate the evidence and weigh it and understand if it's really real and it really says what you're being told it says. And then you can get a passing grade at critical thinking. But you know what? We can do better than passing. We can get an A+ in this. To get an A+ in this, you have to be able to come up with this evidence by yourself. You need to think up these tests and figure out what does it mean. For example, if the Earth is flat, that would have certain ramifications. It would mean things that we could test and see if it's really true. And that's what I'm going to do here. But before I do, I want to lay out some rules to make it fair, so that I could really expect individuals, these average people, to be able to do these tests. So everything, you'd have to be able to do it by yourself. Or maybe, get a couple of friends and do it together. Hook up with somebody in another town for a distant test and do it that way. But we can't rely on something that you need a government agency for or anything like that. So we won't be accepting photos from NASA. You can't independently verify those. And information from textbooks or ancient texts or any kind of stories on the internet will not be acceptable unless they can be independently verified by an individual. So if a textbook tells you a piece of data, that's not reliable unless the textbook tells you how to go and measure that yourself and you can verify it. Then that would be acceptable. So the next one is, we're not all Elon Musk. We can't just build our own rocket and shoot it up into space and take a look for ourselves. So asking for something like that would be unreasonable. I will hold us to $100 per experiment, nothing more than that. So that means I will not ask you to buy a theodolite, I will not ask you to buy an expensive laser, and I will not ask you to book a flight down to Antarctica and go and look at it. Okay, and the last one is we're not all Einsteins. Not everyone can do the math, and tests like these and asking average people to exercise critical thinking would be unfair if I was asking them to do difficult math. So there will be some math. We're going to do basic geometry, do a little algebra, and we'll rely on some simple trigonometry. So if you think you can handle algebra and trigonometry, then I think you're perfectly well equipped to do some critical thinking here. With those rules in mind and the goal of determining for yourself, is the Earth flat? Is the Earth round? Here are 20 tests that I came up with myself that can each individually answer that question. And maybe not all of these are good for you. Some of these are going to expect that you live perhaps near an ocean. Some of these talk about things in different hemispheres. So if these don't apply for your location, I'm not asking you to fly to the ocean to go and test it. Just pick the ones that work for you. There's some in here that anyone can do. So I'm saying that if the Earth is flat or if the Earth is round, that all 20 of these tests will point to that. So I'll go through each one of these now very, very briefly, just to give you the idea of what we're talking about. And if you have any questions about what do they mean or how do I do it or anything like that, or hey, that test isn't applicable because of XYZ reason, then, hey, toss that in the comments. We'll talk it out, and maybe a follow-up video on any of these would be an excellent idea. We could do that. Okay, so let's start. For the first of my suggested experiments, let's start with what is probably the most obvious. We're told that sailors thousands of years ago discovered that as an object went into the distance, it would disappear, and it would disappear from the bottom up. So if we look at this on a globe, as we take this object and move it away from our viewer into the distance, it will go beyond the curve, and our viewer's view of it will be obstructed. And the obstruction happens right here, where the viewer's sight line to the object is obstructed by the curvature of the Earth. And the bottom of the object is what gets obscured first. On the other hand, if the Earth is flat, then as we move the object away, there won't be anything particularly obscuring the bottom of the object, and we should be able to see the whole thing. It'll still be smaller, perspective still applies, but not particularly from the bottom. So that's something that's easy enough to test if you live near any large bodies of water or any other large flat surface. Now, I really don't like this one that much. I don't usually suggest this, but it's so obvious that I really have to suggest it. The reason I don't really like it is you've probably noticed that anytime you take a sight line skimming along the surface of the Earth, that sight line can be subject to miraging and refraction. And you're driving along a hot road and you'll see the road turns shiny, reflects the sky. And that's right here where you're skimming along the ground, or right here where you're skimming along the ground. So you can get some sketchy results from this experiment, but still, go ahead and do it and take a look for yourself. If this happens consistently, if there's many, many observations over time and you get this a lot, then that's good evidence for a globe. And if you take many, many observations and most of them look like this, then that would be your evidence for the flat. What I like to do more, I like to just take it to the next level, which is to just move to a higher altitude. Take your observation down near the ground and see how is that observation affected by just moving to a higher place. Just moving straight up into the air, we see our globe viewer now has a less obstructed, or in this case, even unobstructed view of the entire object. Just by moving straight up into the air, the bottom of our object has been revealed. Whereas if the Earth is flat, we get really no difference. There's very little difference at all in the view caused by moving straight up into the air. And here's one that you hear a lot. You hear this one a lot, that the horizon rises to eye level. Well, if the Earth is a globe, the horizon does not rise to eye level. So you could test that one pretty easily. Make yourself a little level and measure what is the angle between your straightforward view and the angle down to where your view touches the horizon. And what we saw before was that you go to a higher altitude, you just go straight up and do the same experiment again. You should be able to see farther, and the angle to that tangent is steeper. You keep going up, and it goes farther and farther and steeper down. So that should be pretty easy to test. Let's take a look at what that looks like on a flat Earth. Now on a flat Earth, like we saw before, the point where the horizon is would be at the end of the Earth. Now if that's an ice wall, then you should be able to see unobstructed all the way out to the ice wall. You know, maybe there's a mountain or something in here that you couldn't see over. So, you know, look out over the ocean if you happen to live near an ocean, and you should at least be able to see, I don't know, to the opposite coast. Or, you know, whatever it is the farthest point that you could see out into the edge of the Earth. As you go up higher, that angle does get steeper, but it gets steeper at a different rate. So if you measure this carefully, and then you should be able to compare this versus the globe model and see which one was better. Now, this still is not rising to eye level. If you want the horizon to rise to eye level, you have to imagine that the Earth is effectively infinite, that your view out to the point where the water stops and the sky begins is at infinity, and that will cause your view to be at eye level at any altitude. So go out and measure it and see if that's what you get. All this talk about horizon brings us to another one that's generally really quite obvious, and that's why is there a horizon at all? In the globe model, we say that there's a horizon because your view is blocked by the curve of the Earth, that you can't see past the curve of the Earth, and this creates a horizon, where at this point below this you're looking at, you know, the water or the ground below this, and above this point you're seeing free and clear out to the sky out here. So whatever the sky is out here, and below here is the Earth. On a flat model, there's nothing to obstruct your view all the way out to the edge of the Earth. So if you're thinking there's maybe, you know, there's an ice wall here, right? Or, you know, that's just China, right? I'm in California, I'm looking out west. I should be able to see China in the distance, and due to perspective, China will be very, very small and blurry. So extremely blurred, maybe obscured by fog and the atmosphere, and maybe I won't be able to see anything because it's just blocked by the atmosphere. And if that's the case, what I should see is, you know, nice, clean, crisp ocean here that gets fuzzier and blurrier as it's obstructed by the atmosphere until I start seeing just nothing but fuzz and haze at this point. And then ask, can I see the sun or the moon or stars, anything like that? If I can see those and they're not obscured by haze and mist, then why is the ground Why is China obscured by haze and mist if the sun isn't? So check that one out. That was a sunset or a sunrise I was just showing. How does that work? Now on a globe, here we have an observer standing on a globe, and this line represents the horizon. It's tangent to the Earth at that time, and he's looking towards the sun. We're going to say that in this diagram, this is 93 miles off that way. So this is just like where the sun is on this side. It's way off there. So the line towards the sun is effectively a straight line like this. And it's definitely below the horizon here. And then here's sunrise, where the sun line is straight parallel to the horizon. And then as the day goes on, the sun gets higher in the sky, lower again, until we hit sunset. And then the sun is now below the horizon at sunset. So what happens on a flat Earth? On a flat Earth, we're told that the sun stays at a steady altitude above the Earth. It stays over the flat plane of the Earth at the same height. It never dips any lower or higher. So it just moves in a circle. And from a side view, this is us looking at the circle as it goes away. And it never dips down low. So if the Earth is flat, we should see that the sun it starts higher and then it gets lower due to perspective. This is farther away, so it should get lower here and highest here. But the sun never crosses the line of the horizon. It never crosses the plane of the Earth because it's always the same distance above. So we will not get a sun crossing below at sunset or rising up from below on sunrise. Now, before I go any further, I'm going to say this. I'll probably say it a few times. Don't look directly at the sun without eye protection, genuine eye protection. It's not safe. So, do this with the moon. The moon is safe, right? It's not going to burn your eyes. So feel free to do that with the moon, or get yourself a solar filter. Solar filter would be really handy for this next one, where we are going to measure the size of the sun or the moon as they traverse the sky. So we said in that flat Earth model that perspective would change the position of the object. And of course, perspective changes the size. So let's try this out on a globe. Let's do the sun first with eye protection. So at sunrise, here's our observer looking at the sun, and the day moves on. And here's local noon, where the sun is the highest point it can, and then the day moves on and we have sunset again. So how do we measure the difference in the size of the sun during the day? Well, the closest point we get to the sun is right here, and the farthest point we could be from the sun was here at sunrise or sunset. And the radius of the Earth, we are told, is about 4,000 miles. So if the Earth is really 4,000 miles across, then this observer is 4,000 miles closer to the sun than this observer is. And the sun, we're told, is 93 million miles away. So if that's really true, then when this observer, who is the closest, measures the size of the sun, it says, okay, we'll call that 100%. We can do a little bit of math and just see that this observer will see a slightly smaller sun. How small? This size. And that's probably not something we can really measure. So really what we're saying here is that the sun should be the exact same size at sunrise, all throughout the day, noon, all throughout to sunset, same size. The moon is a little different because, well, first of all, you don't burn your eyes by looking at it. And second of all, because it's so much closer. The Earth is still, we're told, 4,000 miles. But the moon, we're told, is 240,000 miles. So 240,000 as opposed to 93 million, that'll make a difference. If this viewer sees 100%, this viewer sees 98%. 98% is still pretty close to 100%, but if we're really careful, you could theoretically be able to measure this difference and verify, see if it's really accurate. You could even use this measurement, if it's good enough, to challenge these numbers. Okay, so what happens on a flat Earth? On a flat Earth, so we're told the Earth moves, or the sun moves around in a circle above the flat Earth, like that. So our view and what happens to our view is going to depend greatly on where we are on the Earth. Let's just put ourselves here under the equator during the equinox. So I'll be in Ecuador here. The viewer's in Ecuador, and here is sunrise 6 hours earlier. 6 hours earlier is right there. So the sunrise, and then during the day, the sun moves towards us, and here we are at noon with the sun directly above us. So the question is, how much farther away is the sun at sunrise than it is at noon? Now, if we know the radius of the equator, we can tell how far that will be. I don't really know if there's a fixed number for this in the flat Earth movement. I'll just take the same radius as the radius of that was given by the globe Earth, which is 4,000 miles. So I don't know. I mean, it's just a guess. It's just whatever. We're just doing this as an example, so it doesn't have to be really accurate. So this is 4,000. That's 4,000. Pythagorean theorem says that's 5,700 miles, give or take. And viewed from a side view, that's this distance. The sun at noon is 5,700 miles closer than it is at sunrise or sunset. So how high up is the sun? Again, I don't know if we have any hard and fast rules for this, but I've heard the number 3,000 miles. So let's say that's 3,000 miles up, and this distance is 5,700 miles. So that makes this distance about 6,400 miles. And to complete our triangle, this is, of course, straight up 3,000 miles. So if this is 3,000 miles and this is 6,400 miles, and this is our 100% maximum size sun, then at sunrise or sunset, we should get something like 47%. And there was a whole lot of just guesses and made up numbers on this, and this is going to vary depending on where you're standing. So plug in the numbers that you want to use. Don't use my numbers, use your numbers, and see how much variation you get. The point really is that you're going to get a lot more variation than the amount we got with the globe Earth. And that should be very easy to measure. With the sun, it's very easy to measure only if you have a solar filter. If you don't have a solar filter and you try to take a picture of the sun, you probably know you just get a big glare. And how are you supposed to say how big that is, right? Okay, so as long as we're watching the sun or the moon moving across the sky, let's time it. Let's measure the speed of the sun or the moon as it moves across the sky. So we have here observer at sunrise, takes a measurement, and sure enough, the sun is parallel with the ground. And then throughout the day, at even intervals, we take measurements of the angle between our local horizon, and the angle of the sun. And we do that at different times of the day. And here we are at noon, here's the local horizon, and the sun should be straight up at that time. And then at sunset, the local horizon and the sun are parallel. So this is a pretty jumbled up little diagram, but if I take away most of the stuff and just leave the green lines, what you see is that the lines are evenly spaced in angles apart. It's the same angle difference every hour. On the flat model, this is the motion of the sun as it goes around in a circle. So your results are going to vary depending on where you are. So let's just take an observer here in Los Angeles. And that's your day in Los Angeles, right? This is noon, then 6 hours earlier, sunrise, and then 6 hours later, sunset. And I've sketched this at the equinox again. Equinox happens to be coming right up. The important thing here, and you'll have to look closely to see it, is that the sun's angular motion across the sky is not steady. This angle is much tighter than this angle. This is a wider angle than this is. What that means is the sun is moving slowly here, and then it speeds up in the middle of the day, and then it slows down again as it dips into the end of the day. So measure that, and if that's what you find, then there's your evidence for that. This diagram sort of leads me into the next idea, which is check out this angle here. Sunrise is here, sunset is there. What's going on with that? Here we are in the globe model. On the globe model, during the equinox in particular, just like the previous diagram was at the equinox, this is my equator, and the Earth is rotating now. The Earth, this diagram, the Earth is rotating around, so rotating around, and the sun is 93 million miles off here. So if I put an observer on the equator, right at sunrise, this is the moment when the sun is shining this way. This half of the Earth is lit in this diagram. So we're showing this half is lit and this half is dark. So this is the moment when our observer is just seeing the sun for the first time and looking towards the sun right there. So let's put another observer a little bit in the northern hemisphere, a little bit further north, like way up in the Arctic Circle. All our observers looking towards the sun, and they're on the same east-west line here, so that all happens at the same time. Let's do some in the southern hemisphere, and that's what that looks like. So, what is the compass heading for each of these people? Let's draw a little north, south, east, west here. So this is due north, this is due south, so that means this is due east. The sun at sunrise on the equinox is due east, no matter where you are. Anywhere you can see the sun crossing the horizon on the equinox, on the globe, it's due east. But what about on the flat? Let's do Los Angeles again, and this time I've rotated that map around so that we can see straight down is south. So we're on the equinox again, Los Angeles again. At noon, the sun is due south. 6 hours earlier, the sun was there. 6 hours later, the sun is there. So this is our sunrise, comes up, noon, and sunset. So let's take compass headings. Take a compass heading to the sunrise and the sunset and check it out. Well, this is north, this is south, this is east, and this is west. So there's an angle here. That's not due east. Equinox is coming right up, so just go out with a compass and measure and tell us, what did you get? What was the heading of the sun at sunrise? You're probably aware that the North Star remains fixed in the sky while all the other stars seem to rotate around it at night. So here we have a viewer on the North Pole looking straight up at the North Star. Now the angle between the horizon and that North Star should be 90 degrees here. But let's go further south and see what happens there. As you go a little further south, the angle decreases. The North Star gets closer to the horizon, and that should continue happening as you go further south until you hit the equator, at which point it's going to hit the horizon. And if you go past that, you won't see it anymore. And the interesting relationship we should get, because we are saying that the North Star is actually way light years up off the top of the screen, these lines point straight up. They don't point at an angle up to the North Star, they point straight up. So we should get a relationship where the angle of the elevation of the star is equal to the angle of your latitude. Now, we're usually told that on the flat version of the Earth that the stars are much closer than that. So at the North Pole, you still see the North Star straight up. But at other distances further south, the angle changes to the North Star, as it did in the globe model, but for a different reason. This time it's happening because the star is close to the Earth. So you get the same approximate result, but the angles are different. And you should be able to use those differences to determine which of these models is correct. In fact, one thing I want you to do right away is try going past the equator, go south all the way to the most southern edge of the flat disk, and look up at the North Star and tell me what the angle will be there, because we predicted on the globe that you wouldn't be able to see it at all. Since we're talking about the North Star in different latitudes, let's try triangulating. In the globe model, the North Star should be straight up off the celestial pole, so the angle between your local horizon and the North Star should be given by your latitude. And that should be the same for everyone, everywhere, very consistent of all viewers. In the flat Earth model, the star is much closer, so any two people in two different locations should be able to triangulate and actually calculate exactly how high up above the flat plane the North Star is. So that's useful. We should be able to triangulate that and calculate exactly, and then we should be able to verify that a third viewer in a different place sees the exact same result, that there should be a perfect intersection of this location, no matter how many viewers you try this with. So I mentioned that the stars, they appear to go around in circles. They go around in circles in the sky, and that's because the stars are fixed, but the Earth is actually going around in a circle. So what I'm drawing here, I'm drawing the trace. This is where I imagine the star appears to be directly above the Earth at that location, and then the Earth rotates. So it's making this star trail in the northern hemisphere, and then there's the North Star, so it's directly above the North Pole. And as we go further south, the star trails get wider. It's a bigger circle as you go further south, as you hit the equator. Now, when you hit the equator, this circle is so big that it goes around the whole Earth, which would make just a straight line across the sky if you were standing on the equator looking up. If you go further south, these circles are going to be getting smaller again. They're going to get smaller again, and we'll see that they're rotating in the opposite direction from the ones we saw up in the northern hemisphere. And the farther south you get, the tighter and tighter these circles get, until finally, if there were any stars near the pole, you'd see them holding still again. So what happens on the flat Earth? On the flat Earth in the northern hemisphere, we get a very similar result. We see that the star directly above this point goes around in a circle in the northern hemisphere, and the North Star hovers directly over the North Pole. That's perfect alignment with the other example. As you go further south, however, you go to the equator. Here we have an equator where this is supposed to be a straight line over the sky in the other model. And then if you go further south, you get bigger and bigger circles instead of smaller circles. And if you were actually to look southward out toward what we said should have been a second celestial pole, instead you're going to see a star going all the way around, skimming near the horizon somewhere, all the way around in a circle. So let's take a moment to talk about satellites. If the Earth is flat, obviously satellites cannot orbit it. So let's check this out. NASA tells us that you can actually go out and see satellites, particularly the ISS. The ISS is low and large, so they say. So you should be able to go outside and you look it up where it is, find a nice dark place that you can go to sort of near yourself and go out and take a look. And if they're telling the truth, then this ISS satellite will be visible as a streak of light, a dot of light crossing the sky. If the Earth is flat, it's really hard to imagine how that could be possible. How about moon phases? The standard diagram of the moon phases looks something like this. An idea is that when the sun shines on the moon and the side facing us is what we see, right? So in this case, the new moon the lit side is the side facing the sun, and the dark side is facing the earth. And here's the quarter moon where the lit side is facing to the left and the dark side is facing to the right, and we look up from the earth and we see both halves. And the full moon, we see the side that's lit by the sun. On the flat earth, I'll put the same moons in a diagram around here, showing that the sun and the moon appear to be on opposite sides of their orbits during the full moon, and then they're very close together during the new moon. But if there is a relationship, as I'm saying that I think there is, between the location of the moon and its phase relative to the sun, then I don't know what the explanation for that might be if the Earth is flat. Okay, how does the phase of the moon compare when you look at it from a different place on the Earth? Here I have 3 observers looking straight at the moon at the same time, and I've set it up so the northern hemisphere viewer sees our little quarter moon where the bright side of the moon is up top, this top where his head is, so up at the top, and down near the observer's feet is the dark side. And here at the equator, we see the same phase of the moon approximately, but the bright side and the dark side are oriented differently. To him, the bright side is on the left and the dark side is on the right. And then as we go all the way into the southern hemisphere, we see approximately the same phase, the same quarter moon, but now the bright side is at the viewer's feet and the dark side is at the viewer's head. So on the globe, the phase of the moon does not change as you go north to south, but it does rotate. It turns upside down if you go in the southern hemisphere. On the flat Earth, let's try the same thing. Here we have our half moon. In the northern hemisphere, it looks something like this. So we see our quarter moon here, viewed from way up in the northern hemisphere. As we go down further south, and I haven't reached the equator yet, I'm just going further south, we see that the phase of the moon is changing dramatically. And then let's go all the way into the southern hemisphere this time. And now in the southern hemisphere, we're seeing a new moon. In the northern hemisphere, we were seeing a quarter moon, and then it got down to a crescent moon, and now it's almost a new moon down here in Australia. I don't see any cause for the phase of the moon to rotate upside down like it did before, but the phase does change. So take a look at that. Compare that. Is the phase that we see the same phase depending on how far north and south we go, and does it turn upside down? As long as we're talking about moons, can't skip this one. The lunar eclipse. This is what the globe says happens with the lunar eclipse. The shadow of the Earth cast back behind the Earth. You know, the sun's over here, so the shadow of the Earth goes that way. If the moon happens to pass right through it, then the moon gets dark, and that's an eclipse. And here's that situation shown on the flat map where the sun's on that side and the moon's on that side. And, you know, we honestly, I don't think we even knew what was causing the phases of the moon and whether the sun's light can even hit the moon on the flat Earth. So I don't know what conclusions we can draw, but we do see lunar eclipses, and they always happen during this alignment. Or at least that's what I say to do. Go out and check. Do the lunar eclipses always happen during this alignment? And if so, why? All right, changing tack quite a bit here. Let's do purely ground-based experiment. In this case, what we're going to do is we're going to try and get an estimate of the distances between cities on the Earth. And we do that simply by looking up flight times for direct flights. Try to go shop for flights and connect a bunch of different cities on the Earth. I'm showing Sydney, Australia. I'm showing 3 different flights connecting through Sydney, Australia. as they go over the globe. Here's the same 3 flights out of Sydney, here, here, and here. And I think you'll find that anything that you can make work on the flat map cannot work on the globe map, because you can't unroll a globe and get the same results. So by doing this, you should be able to show which of these two is accurate. This one's relatively easy if you have both tall buildings and a clear view of the sunset. So anytime you have a tall building that has an unobstructed view of the horizon at sunset, you'll see a shadow go up the building. And as the sun sets, the shadow climbs up the building until the building is completely dark. But that only happens on a globe Earth. Satellites, back to satellites. Satellite dishes. We rely on those for cable TV all over the place. So why don't you drive around your city and take a look at all the various satellite TV dishes that people have on their homes, and see if you can make any generalizations about them. Do they all point exactly in the same place? Do they group into things that they all point at? Some are pointing this way, some are pointing another way. Are they all pointed south? Are they all pointed north? Within what degree tolerance do they vary? Are they what height do they seem to point to? Check these things out, and from that I think you can infer a great deal about the radio source that these are pointing at and where that must be in the sky. Foucault's pendulum. We are told not only that the Earth is a globe, but also that it rotates. So one way of showing that it rotates is to swing a very large pendulum, a pendulum large enough that it can maintain its swing for a very long time, perhaps some hours. Over the course of those hours, if the Earth rotates beneath the pendulum will show it. And for my last example, here's one you can just do from the comfort of your computer. Just look up old weather systems, old storms, tropical storms that have happened in the past, or watch current ones as they unfold on the Weather Channel. You'll see that the storms always seem to rotate like this. But which way do they rotate? Do they always rotate in the same direction like this? Or do sometimes they seem to rotate in the opposite direction? Can you find any pattern? Which ones rotate one way and which ones rotate the other way? And I suggest that you can find a pattern that indicates the flatness or curvature of the Earth. So there are my 20 easy tests for whether the Earth is flat or round. But I didn't actually tell you whether the Earth is flat or round. I just gave you 20 examples of how to answer the question for yourself. To be honest, some of these experiments were so obvious that I think you've probably jumped to a conclusion by now, and yeah, the conclusion is pretty obvious. The real important thing of all of this yammering on is that the question can be answered very definitively and, in fact, very easily. It's not difficult to answer this question. So if you encounter someone who says, oh, well, there's no way to be sure. You'll have to fire me up in a rocket. And there's no way to be sure unless I can go up in a rocket and look for myself. That person has just failed. They have failed at critical thinking. There's absolutely plenty of ways that we can definitively, easily answer this question without going up in a rocket. And what I'd really hope is that using this as an example, you can jump off of this by yourself and take this into other questions that come up. And is climate change real? And will vaccinations kill my children? And all kinds of other questions that are going to come up for you in your life and important decisions you're going to have to make. And you can use these same ideas to answer those questions for yourself and get the right answers. And as you practice with it, as you experience this and you try figuring out the truth from the falsehoods. I'm hoping that you will refine your baloney detector. You'll be able to start to identify patterns where who is trustworthy and who is not, what sorts of claims are likely to be true, and which sorts of claims are extremely suspect. And just refine that ability. It'll serve you well in the future.